Welcome back, everyone, to the afternoon session. Our first speaker this afternoon is Lee Guo from Rutgers University in Newark. He's going to be speaking about Volterra integral operators and generalized Reynolds algebras.
Okay, and good afternoon, and thank you. I would like to thank the organizer for giving me the chance to speak here, and thank Richard for the nice introduction. Okay, so actually this work is a joint work with Richard and Yunnan Lee. Yeah, so is this loud enough? Okay. All right, so this work kind of started when it's like about a little bit more than a year ago, when the three of us get together to try to explore some potential algebraic structures for integral equations. Actually, there are already some structures for special integral equations, but we try to look more generally. All right, so this is kind of an update of the abstract. So I decided to use this whole page display instead of item by item, because I find that item by item approach is kind of testing for the memory of the speaker. You know, have to remember what's the next to come. So we in particular consider special kind of integral equations or integral operators called Volterra integral operators. With integration, as we know, it has upper limit, lower limit. Okay, so usually we fix the lower limit, and then upper limit. If upper limit varies, it's called in general a Volterra integral operator. If upper limit is fixed, then it's called a Friedholm integral operator. Okay, these are the two kinds of integral operators. And then when they live in an equation, it's called either a Volterra integral equation or Friedholm integral equations. And then you can have the variable function living in different places, and then they are type 1, type 2, and so on and so forth. Okay, so we consider in general Volterra integral operator and the equations. So talking about the integral operators, there is actually a very simple integral operator that satisfies the so-called Rota-Baxter identity, or is a version of integration by parts. So here, maybe I should remind ourselves why there are so many different kinds of integral operators or integral equations, rather than like differential equations, whose algebraic study is the subject of this conference. So everybody works with very nice differential algebra, differential equations. Well, that's because, as we know, integrals are defined in different ways. Okay, so further they are so-called kernels. So because of all this large variety of integral operators, there are a very large variety of integral equations. Okay, so some of them are really too general to study. Okay, so for that matter, there are really quite very few types of integral equations that have been studied in the literature. Okay, so and we try to also put that into a general algebraic framework. Okay, so all right, so now let's start with kind of a definition of what is a Volterra integral equation. All right, so here with a Volterra integral equation or operator, well, same with Friedholm integration operator. It has a kernel. So this k is a two-variable function. It's fixed. All right. So the one variable is the dummy variable in the integration. One is the variable for the equation. Okay. So it's the variable for the for example, for the solution, okay, that the one is looking for. Then here we have a fixed lower limit, upper limit can vary, And as I mentioned, if upper limit is fixed, then usually it's called a Friedholm integral operator. Okay. So, and then there are different kinds of integral operators depending on this kernel. So kernel, for example, can be separable, meaning it can be separated into product of two one-variable functions. And another further simplification is that it actually doesn't depend on the so-called dummy variable. Okay, so in that case, we call the kernel phantom, all right? Because we could call it the dumb variable, but it really sounds kind of too dumb. So we would rather more like an artistic name, like fountain in the opera, right? Okay, so we call the fountain integral operator. Okay, so there are some classical examples of Volterra's integral operator. So one is Volterra's own model. Okay, so of population control. So this is the equation where we have A, B, and C standing for birth rate, crowding coefficients, and toxicity. Okay. So then another one, which is not exactly some kind of algebraic integral equation because of the fraction powers. Okay, it's the Thomas Fermi equation. Okay, so there are classical background for integral equations. All right, so and there are quite much study of analytic study, okay, or numerical study of integration. And further, so I've now said this is the only approach of integral equations or involving integral equations. There are actually some other literature or other directions for integral operators and integral equations. For example, multivariable integrals. Okay, so for example, let me just mention the work of Marcus Rosenkranz, right? So they and Regensburg. So they study integration with multivariable and some linear transformation. Okay, so all right. So now, where does the algebraic structure comes in? So let's start with a simple case. That is the Rota-Baxter algebra. Okay, so Rota-Baxter algebra, for those of us who probably see this for the first time, it's a generalization of integration by parts. Okay, so it was the equation or the notion was introduced in 1960 by Baxter. Okay, so who is a mathematician doing probability, and in his study he identified such an operator when this lambda is -1. Okay, so then he immediately realized that okay, one doesn't have to have a fixed constant, one can have a variable constant, and with this constant is 0, one actually has an integration by parts formula. So this is a version of integration by parts formula. So in that sense, okay, so one can say that the Rota-Baxter operator is at least represents a special case of integration operator. Okay, so that's actually the motivation for me to get into this field. When I worked with Bill Keir, that's like 20 years ago, we thought, okay, to study algebraic structures of this kind of integral, this kind of algebraic structure, and only to be reminded by Rota that such identity in a general form already existed 40 years ago. Okay, so but nevertheless we continue to study this. So this provides a nice algebraic framework for a simple integration integral equation. Okay, that's what I'm going to get into next. Okay, so but for this to represent integral equation, there are only one kind of simple integral operator, but the integral operator doesn't have to be unique in the equation. So we have this more recent notion of matching Rota-Baxter algebras, which can have multiple linear operator. We individually they all satisfy Rota-Baxter operator, but there is also this mixed relation. Okay, so you can have two linear operators. When they multiply together, they have this kind of compatibility, this kind of mixed Rota-Baxter identity. Okay, so we really only consider lambda is 0, so we only have this three-term equation. All right, so those three-term equation, or this identity actually captures the class of integral operators or Volterra integral operators. Okay, so namely Volterra integral operators with so-called phantom kernel. Okay, so phantom kernel again means that this kernel only depends on t, not on x. Okay, so in that case, by the matching Rota-Baxter identity, you can have multiple phantom Volterra operators, but they will be compatible in this way. Okay, so what does this mean? This means that if you have two such integral operators multiply with each other, it can be expanded. Okay, so these two operators are kind of parallel. These two terms are nested. Okay, so this nested. So in a way, so this means that if you have like a degree 2 operator, degree 2 operator term, namely if you have two operators multiply with each other, it can be put into a nested form. Okay, so that's the kind of linearity that we are looking for. All right, so in other words, there will only be high power of these integral operators. Okay, so okay, so I'll bring back the structure of such matching Rota-Baxter operators later, but for now, as on a kind of more basic level, let's see what happens with other Volterra operators. Okay, so now if the kernel is not phantom, okay, in other words, if the kernel involves x in any way, then it's almost never Rota-Baxter operator. Okay, so we'll give some kind of evidence in the opposite direction in several level. Okay, eventually we'll give a definite result to show that this is true. All right, but for now, let's just look at an example, right? So for example, you just have x here, all right? And we just take a very simple function, fg both 1, and then we check this Rota-Baxter relation, right? This is left-hand side, this is right-hand side. Okay, so again, it's like an integration by parts. So then just by direct computation, we see that the two sides are not the same. All right, okay, so that means that this particular Volterra operator does not satisfy integrated by parts relation, okay, or Rota-Baxter relation. Okay, so so you might think that this x is quite innocent, right? So for example, if you look at here, right? So this x can be pulled out. Okay, you might think, okay, so what's the difference between this and just integration over nothing, right? But that happens to not be the case, okay, which kind of misled us at the very beginning of our study. So that happens. What happens is that when you have nested sum, this x behave in a very different way than if x is t. Okay, so that's what causes this difference. And more generally, we have the following theorem, namely, if we have a separable kernel, and if this kx is non-trivial, okay, it's not constant, okay, so then we have for the corresponding Volterra integral operator, in order for it to satisfy a Rota-Baxter identity for a particular f and g, okay, we are not looking at arbitrary x and g. So if we have a given f and g, in order for the Rota-Baxter identity to hold, eventually basically means that it has to hold in a trivial way. Okay, namely both sides are already 0 individually. Okay, so again we'll give further result in this direction. Okay, this shows that once you pass this trivial case of phantom kernel, then okay, the classical result of integration by parts is not going to work anymore. Okay, so that's pretty big picture. But luckily, we don't have just one operator identity. We have many operator identities, and we don't have just one Rota-Baxter algebra. We have other algebras with operators. Okay, so the next operator comes to rescue is called D-Reynolds operator. Okay, so if you look at identity, you'll see that the first three terms is the same as the Rota-Baxter operator or integration by parts formula. And there is also a third term, except that the third term, okay, instead for having a constant here, it's like higher order of the operator. Okay, so R times R, F times R, G. Okay, or R applied to F, R, F times I, G. Okay, so this operator actually arises independently at the end of 19th century. Okay, it's many years ago from the study of Reynolds in fluid mechanics. Okay, so that's totally from different direction. And later on, it has some other names or related to other operators like average operator. It has attracted attention of quite well-known mathematicians like Birkhoff, Rota, and so on. All right, but mostly they are studied from an analytic point of view, and here we still consider it from algebraic point of view. But then again, we want to use this operator to bring the study up to the level of algebras. Okay, so all right, so now so from this operator, we consider this separate operator with separating kernel, right? So then we found that not only this has a generalization, and it also has kind of a twin on the differential side, okay, related to differential algebra. Okay, so we look at this identity, right? So this is, if we look at the first three terms, it's really just differential algebra, and then it has this one extra term, okay, depending on the operator itself. Okay, so then what we find in this setup is that if we have a separate kernel like that, if we define the differential operator, okay, so this is not ddx, but nevertheless it is a differential operator, okay, satisfying Leibniz rule. Not satisfying Leibniz rule, satisfying Leibniz-like rule, okay, so which is given by that, okay, and then together it satisfies the following more general Reynolds type operator. Okay, so which is still quite nice. Okay, it says that we can study this kind of more pretty general Volterra integral operator, right, with pretty much arbitrary separating kernel in this context. Okay, so that's kind of our first kind of major kind of breakthrough in this direction. Okay, namely, it gives some hope to give algebraic study of integral operators and integral equations for some non-trivial situation. Okay, so now let's look at some kind of special cases and some examples. Okay, so first of all, this differential operator at 1, okay, so is given by, this should be x, okay, this should be x, okay, so at x is given by this formula, okay, so therefore, if k is a constant, then the derivative is 0, all right, so dk1 is 0, okay, all right, so now what does this mean? Okay, this means that if we jump back to the equation at the bottom, so that means that this term is 0. So that means that we have what? We have integration by parts. Okay, so that further enforces the claim that I made earlier that for the integral equation with several kernel can be expected to be a Rota-Baxter operator only when the kernel is Fulton. Okay, so that's this. And then we go to a very specific example. This example actually was in the very early study of Rota. Okay, so and probably can trace back to Reynolds himself. So namely, we have this this kernel. Okay, it's apparently separable, and this D term is 1. Okay, so it satisfies this canonical Reynolds operator. Okay, so as I mentioned before, this can be traced back to the study of fluid mechanics over 100 years ago. Okay, all right. So this again, so this gives some examples, evidence, and results that there could be some good algebraic theory or structure coming up from integral equations. Okay, so so this is like the first level of presentation. Okay, so I try to put on basic algebraic level, working with concrete equations. But what we're going to do next is to actually give some algebraic structure, okay, that describe this kind of integral equations. Okay. All right. So again, make an analogy with the differential algebra that everybody here is working on. So what we know is that differential algebra is an algebraic study of differential equations. Okay, so we take differential equations from analysis, physics, or what else. Okay, so we want to give an algebraic. Okay, or in a way, it's like a rigorous study of differential equations, right? Because when you write down differential equations, okay, so what is a differential equation? Okay, so it's like you know the meaning, but it's really hard to say what is the definition unless you put it in an algebraic term. Okay, it's the same way as you can write down a linear equation. Okay, so what is a linear equation? Okay, probably the only way to say is what is a linear equation is to put it in a linear algebra context. Okay, same with polynomial. Okay, all right. So here it's similar. So if we want to consider integral equation in a very rigorous or general way, so we probably want to know, okay, what is algebraic integral equation, or what is the integral algebra for that matter? Okay, so here I give kind of very rough brush. Okay, but try to be general. Okay, what is integral equation? Okay, so if we move every term to one side, okay, so we have expression that equals 0, right? So that means that the left-hand side is some kind of operator, right? That we want to study what's the annihilation, right? What's the kernel of that? Okay, so if we have a differential equation, okay, that solution we want to study the annihilation of that differential equation, which is in essence expression in free differential algebra, right? So you take an expression from differential polynomial, you say, okay, this equals 0. That's differential equation. Okay, so you may take this as a complement to everybody here working in the field. That's probably the only right definition to define what is differential equation. Okay, so likewise we want to do something for integral. Okay, so now what is the integral equation? Well, so it should have what? So first of all, it should have some integral operators, okay, which involves the kernel, which involves limits and some other constants, right? And it should involve some coefficient functions, okay, which can really be actually already differentiated and integrated. But they are not what we are looking for. But then we should have a set of variable functions, okay? So those are the things that we want to solve or to annihilate. Okay, so roughly speaking, that is kind of what is an integral equation. Okay, but how do we actually construct, right? How do we define? So as I put earlier, so this is more or less how people would think analytically or on a basic level what is the integral equation. But we know that we can do better, right? So let me give a little bit more detail, even though it looks kind of trivial for you here, but it might give us some hint on what to do with integration aspect. Okay, so as I mentioned earlier, so we studied algebra from elementary school, but what is okay? What do we do with algebra, right? So we study polynomials and so on and so forth. Okay, but really the rigorous way to say what is algebraic equation is to say, okay, so we have a polynomial, right? So, but what is polynomial? Polynomial is defined as a realization of what free commutative algebra, right? So we have free commutative algebra. We have a realization as polynomials. That's the way to kind of encode to represent any algebraic equation. Okay, so it has a variable to solve. It has coefficients, okay, and then right. So the keyword is free commutative algebra. Okay, so free commutative algebra is where algebraic equation lives. Okay, and for differential equation, okay, so again it's similar. All right, so you can have a set of functions. You can have a set of variable functions. You can have a set of coefficient functions. And you can have a set of operators, differential operators. And so now here I want to emphasize that the coefficient function itself may already be a differential algebra, right? Okay, so we are looking at the differential algebra in a relative context. Okay, so it's a differential algebra with coefficient in another differential algebra. And then, as I mentioned a couple times already, so the way to look at differential equation is to say that we have expression in the free differential algebra, okay, realized as differential polynomials. Okay, so that's the starting point for the rest of study. Okay, so with that in mind, so we look at again, okay, what should be our integral algebra? Okay, so the integral algebra, okay, should be okay. I mean, so integral equation should be an expression in a quote-unquote integral algebra. Okay, so integral algebra should have the ingredients we had earlier. All right, and then potentially have some identity that we can distill from the real life integral equations. Okay, so then at the first approach, okay, and to be very general, we just say that okay, we have a bunch of integral operators. All right, but in general, we cannot really expect the differential operator to have much of identity. Okay, so then we just say okay, so what if we don't have any identity? Right, we just have a linear set of linear operators acting on algebra, and this is by itself a category. Okay, so it's what I call the operated algebra. Okay, but it's already can be traced by Kirsch in the 1960s, and where he called omega algebra. Okay, but then so we look at this operated algebra. So which is really just an algebra with a set of linear operators. Okay, these linear operators, at least for now, we don't require to have any property. Okay, so in this context, I constructed these free objects. Okay, so by several means. Okay, by bracketed words, by root trees, and by Morgan path. Okay, so there are kind of one-one correspondence between these objects. So you have a different way to visualize them. Okay, and so they you can say okay, here that's the kind of probably most general context you can think of where you can expect equation to live in. Okay, or some integral type of equation to live in. All right, but here the coefficients are constants. Okay, and as I mentioned earlier, so like for example, to study differential algebra, we have the coefficient with differential structure already. Okay, so in other words, we want to have this algebra with coefficients in the same category. Okay, so all right, so that's one thing that we did in this paper, in this journal paper. Okay, we studied this operated algebra with operated algebra coefficient. Okay, so you might be wondering how that look like. Okay, so I won't be able to give a detailed presentation of that free structure, but I can give some examples here. Okay, so these are some examples where you can visualize these kind of monomials in a operated algebra, in a free operated algebra. Okay, so they are given by trees. So each vertex, you can think each vertex, internal vertex as an operator. Okay, so here alpha, beta, they are operators. Okay, x, y are the variable functions. All right, so every time you apply the operator, you insert a root. Okay, so for example, you can have these two terms. When you apply another operator, that means you're grafting these two trees and add a new root. Okay, and if you have alpha beta on the leaf already, that stands for the operator applied to the identity element. Okay, so this gives nice representation of this kind of potentially integral equations or monomials in a very intuitive way. Okay. But that general context is not very useful, okay, because it's really too broad. Okay, so now we step back a little bit and put in extra conditions. Okay, so a little bit at a time. All right, so we go back to the case where we have Volterra integral operator with fountain kernel. Okay, with fountain kernel. And in that case, we know that it satisfies this matching Rota-Baxter algebra. Namely, each one is a Rota-Baxter operator, and then there is a mixed compatible relation. Okay, and in this case, instead of having this huge structure we had early in the previous slides, we can have a more compact form. Okay, more compact form defined as follows. Okay, so this is a bit technical. So I'll just write down to show you that I'm just bluff air. Okay, so but here you can visualize. Okay, so each tensor factor you can visualize that as an operator. Okay, so this is the operator with kernel omega 1, for example. This is the integral operator with kernel omega 2, and so on and so forth. And each one of each u1, u2, they are kind of functions, either constant function or variable functions. Okay, so we use this to stand kind of monomial of integral equations, and then you can define multiplication. Multiplication is given by so-called shuffle product. Okay, so now you may say, how do you know it's given by shuffle product? Well, it's given by shuffle product in principle because the operators satisfy the Rota-Baxter relation. Okay, so it's like in one variable case, once you have a Rota-Baxter relation, you can reduce all the product of operators into nested one. Okay, so here is nested. Okay, so you have all the nested integral expressions, but you don't have products. Okay, so that's a way to, I take that as an algebraic approach to this kind of problem. Okay, so we define this, and with the shuffle product and with the linear operator given by this form. Okay, we have the free, so-called free matching Rota-Baxter algebra. Okay, generated by V. V is the space of unvariable functions, and A is the coefficient. Okay, so A is a coefficient algebra. Okay, so we have that. Now with this, so what we can say is the following: is that we can put this. We can say two things. One is that we can put this Volterra equations with fountain kernels into this framework. Okay, at first we can put it in this big operator algebra. Okay, but because of this matching Rota-Baxter relation, that the algebra actually descend to the sharper algebra I just described. Okay, so that's one. Okay, the second thing is this operator linearity property. Okay, which I think is pretty important. Okay, what does this say? This says that okay, so if we have an integral equation, it's called operator linear. Okay, if there is no product of integral operators. Okay, so with differential equation, we said that differential equation is linear if the variable function and its derivatives all appear to the first order, right? And a total order, a total degree. Okay, so and of course we know differential equations they are linear, they are non-linear. Okay, it's impossible only to consider linear case, but in the equation case, we actually can do that. All right, so we cannot just be absolutely linear. Okay, there could still be functions multiplied with each other. Okay, so for that matter, you may even have transcendental functions. But in terms of operator-wise, it is going to be linear. Okay, so that's I think this is a useful property. Okay, so when we write down integral equation of this type, okay, you don't have to say, all right, so how I'm going to you don't have to consider any equation with terms that are products. Okay, so you only have this kind of these iterated integrals. Okay, so that's what this theorem says. And further, not only is it iterated, and also between any two integrals, there has to be a variable function. Okay, if it's not a variable function, then you can still replace by another one which has variable function. Okay, so that's what this second statement is saying. Okay, so for example, if we go to this Thomas Fermi equation, so we look at this. All right, this is already nested. Okay, so this is already order one, but in between there is no variable function. Okay, so then we can do a simple integration by parts and express that in terms of that. Okay, so now this would be a integration where there is always a variable function behind our integration. Okay, so that's the nice property of this type of integration, integral equations. Okay. All right, so again, that only applies if we have so-called fountain kernel. Okay, that namely the kernel only depend on the dummy variable. Okay, so if not, okay, so we explained earlier that there's still hope. Okay, so if the kernel is separable, then the operator satisfies another type of operators, namely Reynolds operators and generalization. Okay, so then kind of motivated by the previous case we consider, where we can actually construct free objects, and we can basically tell what are the general forms of this type of integral equations, right, with fountain kernel, and then we try to do the same thing for this type of integral equations. Okay, namely for integral equations with separable kernels. Okay, but here we can run into some difficulty. Okay, because let's take a look of this Reynolds identity. Okay, so this is kind of a simplest case in the context we consider. So we have some difficulty because the left-hand side, okay, which in the rewriting system is supposed to be the principal term, okay, reduced to a three-term sum where the third term has the same monomial. Okay, so that means that if we want to apply this equation to do reduction, then this term is going to repeat over and over. Okay, so if we do some simple computations, basically it means that this power, outside power of operator is going to be increased indefinitely. Okay, so at the end we more look at the series, okay, instead of sum. Okay, so in particular, this probably is not even terminating. Okay, so that poses some challenge. Okay, if we want to construct a free object, right? Because as we know, algebra we work with finite operations. Okay, so all right, so so what we do then is that we try to introduce some topology. Okay, so that we can talk about series and convergence. Okay, so that we can still use some algebraic term to study this or to give algebraic study of this type of Volterra integral equations. Okay, so so we did that. Okay, we construct this free operated algebra and complete operated algebra and complete Reynolds algebra, and we can prove some property for so-called pro-linear. Okay, pro-linear. Pro-operator linear property. Okay, so in other words, we probably need to consider infinite sum. Okay, but that infinite sum has some convergent property. It's like power series. Okay, so that's the part of the work, and then only recently, so this work was delayed. So only recently, actually, we found that maybe we can get rid of that. Okay, maybe we can get over that. So this last part is work in progress. Okay, that we are still on the discussion. So, but what we can do seems to be that actually we can probably get rid of this pro part. So we can have really finite linear sum, okay, linear combination of terms to describe this free, Volterra integral algebra. Okay, so with separable kernel. Okay, so that's yeah. So that's pretty much what I want to talk about. Okay, so let me at the end give you some reference and give you thank you for your time. Okay. Yeah.
This was the Reynolds, the Reynolds stuff, right?
Yeah.
Okay, this is when we talk about the Reynolds fluid mechanics.
That's right. That's the
greater Reynolds number.
Yeah. So. Yeah. So it was a very popular subject to study in the 60s and 50s, 60s. So for example, Rota studied a lot. Volterra studied. So they found that. So actually, in a survey article of Volterra, he actually said it would be an interesting question to study algebraic properties of Reynolds operators. For example, he specifically mentioned, for example, the free objects. He actually posed that question. But it took a long time for it to reach the algebraic community.
Could you say something about the last paper?
Oh, okay. So, yeah, last paper is the following. Okay, so let me go back to to this identity, right? So I mentioned that for us, okay, so once we pass through the first stage of Volterra operators with fountain kernels, where they can be realized on the multiple Rota-Baxter algebras, we have to deal with this type of Reynolds identity. So then, to kind of give algebraic context for those equations, we want to study like free objects, right? So for the free objects, as I mentioned, if we go into this rewriting direction, in this direction, then we run into loops, okay? what we do here is that we give topology. Okay, we give filtration to kind of make that work. Okay, so why we want to insist on doing this direction because of the linearity. Okay, because we want to say any product of operators will become a nested one. Okay, eventually. But for the free object itself, doesn't have to go this way. Okay, so here instead one can take this as the highest order term. Okay, because this obviously has operator term operator order 3. Everybody else has operator order 2. Okay, so if you take this as a leading term and rewrite in the other direction, okay, that pretty quickly give you a kind of convergent rewriting system. Okay, but then to prove that it's confluence and therefore give you a free object, that's still non-trivial work, but that can be done. Okay, so this actually come from discussion with William for this idea, and that's where we get this paper. So in this paper, so in other words, we use another way to construct the free Reynolds algebra. Okay, so it's different from the one that we are on the discussion in this talk. Okay. Yeah. Well, potentially, right? So you have one free object, you have two constructions. There must be isomorphic. Yeah, and there must be isomorphic, and it has to be a canonical isomorphism, right? Sending generator to generators. Okay, very good question. But I'm pretty sure you will see immediately that this connection is highly non-trivial. Okay, so which could give very interesting identities. To make analogy, it's like in symmetric functions, right? So symmetric functions is very useful. Okay, largely because, if I don't say mostly because, it has several canonical bases, right? So elementary, fundamental, power. Okay, so they are all polynomial generators of the same algebra. Okay, so then if you have one expression, they can, so even just for these different classes of bases, they can be expressed by each other. That gives you a large number of combinatorial identities. Okay. For this, we haven't even looked at it. so it's just your question, and I'm responding to that. Yeah. Okay.
So on the title of the last paper, we're using bracketed words as the basis of the tree, right?
Yeah. So we use both.
What are the basis elements in the
Okay, in the new approach, so bracket the words. Okay, so we can put this way. So if we don't put a condition on the operator, okay, so then the bracket words. Okay, so what is the bracket words? Okay, roughly speaking, you start with a set of alphabet. Okay, you can multiply the alphabet in an arbitrary way, which gives you, give you all the words. Okay, which give you free, semi-group polynomials and so on. But when you have an operator, you put brackets. Okay, so every time you apply the operator, you can imagine you have bracket. Okay, so this bracket words actually gives you a very concise way to construct free operated algebra. Okay, so if you have multiple operators, you just take multiple brackets. Multiple indexed or decorated brackets. So that's for arbitrary operated algebra. But now, since Reynolds algebra has certain defining identities, okay, so the free Reynolds algebra would be quotient of those algebra of bracketed words, okay. So but just have a quotient is not interesting for algebra. We want to have a kind of a basis, okay. So in other words, we want to have some subset of these bracketed words, which modulo the quotient actually give you a basis of the quotient. Okay, so that's where this is. Yeah. Yeah. For power series, in the other approach. Oh, so in this, well, the basis would be would be kind of similar to the one I described here. Yeah, there should be string of tensors, except that you have infinite many of them. Okay, so you have like a power series. Okay, yeah, you have power series. Okay, so I have to start this. Okay, so
This
yeah.
is more general. I mean, this has matching Rota-Baxter. The other one, you don't have.
Yeah. Okay, so yeah, nice observation. Indeed, so for once we got in Reynolds, we haven't considered multiple cases. We only look at one Reynolds operator. Yeah, because it looks like that is enough to keep us busy for a while.
So could the bracketed rows be also done in the matching setting?
Yeah, you can put it in that context. Yeah, but that bracket is not that. But bracket wouldn't be so interesting. So basically, you just put a nested bracket. So
you're saying that you have to use the series approach?
Well, I mean, so that's at the very end. So actually, it appears that maybe we don't need a series approach. So which is good news. So in other words, this iteration, okay, of linear operators or random operators or integral operators actually may be transferred from acting on the variable functions to constant functions. So at the end, you can do everything, okay, pretty much everything in the coefficient ring. So you just have to do a lot of integrations for the coefficient function, but the equation itself could still be just fine. So that's what we found recently. Okay, so yeah, at first we thought, okay, so we need to work with completion, and it's almost done. But then, okay, we realized this, and I said, okay, so let's work on this. So that's
very big. You're saying that even if the kernel is not patterned, the system somehow can be hope to be transformed into a system which has random kernels.
not a final kernel. So kernel, you cannot change the kernel, but you can have similar structures. So we can hope to still have similar structures. Namely, you still nested integral,
right,
and finite sum of nested integrals. So right. So eventually, we hope to show, for example, the following property that any Volterra integral equation with separable kernel can be expressed as equation that only has linear or operated linear terms. So right. So I don't know the analytical literature of integral equation very much, but it seems that people in integral equations community mostly they just study linear one. Okay. So maybe intuitively they already know probably they only need to study linear, or maybe they don't. But with this result, we can ensure everybody that you only need to study linear, okay? Because everything